Hello everyone. So in the last lecture we discussed the generation and recombination process very briefly, and also we have discussed different concepts associated with that. We have seen how generation and recombination is, or how generation and recombination can take part in various semiconductor physics related phenomena. Today we will focus more on recombination process, and there are different types of recombination process. We will see what are the expressions of different recombination processes, and majorly we will discuss about three different recombination process. The first one is Auger recombination, and then we will go to indirect recombination, and finally we will also discuss very briefly about surface recombination, and how these recombination processes are actually influencing the semiconductor physics is something that one should know before they go for a for designing a semiconductor device or semiconductor device related sensor. So let us start this lecture and go through these topics one after another.
So we already have discussed generation and recombination process in our previous lecture and different types of generation and recombination. In this particular lecture, we will see uh, the expression associated with recombination. So let us begin with the direct recombination, band-to-band direct recombination process. Now, in case of band-to-band direct recombination process, the electrons generally directly jump from conduction band to the valence band and then recombine with a hole. So the recombination rate R in this case can be given as a constant into the concentration of hole and the concentration of electron. Now if you look at the recombination rate for excess carriers, or you can say excess recombination rate R dash, you can write it as R minus R0. R0 is the recombination rate under equilibrium, and you can further put the values from the first equation. Then you will get an expression like this: alpha into P into N minus P0 N0. They are equilibrium concentrations. Now, in this case, P is nothing but P0 plus delta, where delta is the excess carrier concentration, and N is nothing but N0 plus delta, where delta is again the excess carrier concentration. And in both the cases, delta is same because excess carriers generate in pairs, right? So excess carrier generate in pairs. So the number of holes will be number of electrons as far as the excess carriers are concerned. Okay. And this N0 and P0 both are equilibrium concentration. If you replace those values in this equation and if you simplify, then you will find an expression like this. That is, R dash is equal to a constant into P0 plus N0 plus delta. You can do it in your home and can check. You'll find an expression of this kind, right? Now, in this particular case, the value of P0 is much less because they are minority in case of n-type semiconductor. Let us consider n-type semiconductor in this case. Okay, so we are considering n-type semiconductor. So P0 will be minority, and the excess carrier concentration will be much less than N0 because we are considering low level injection. Okay, so in case of low level, we already have seen that the equilibrium concentration is very high compared to the excess carrier concentration, and N0 is majority carrier. Okay, so it's majority. So obviously the majority is much higher, and excess carrier concentration doesn't affect the majority carrier concentration in case of low injection levels. That is what we already have seen. So we can ignore the term P0 because P0 is minority, and delta because delta is excess carrier concentration, and both of them are significantly less than that of the majority carrier concentration N0. So we will have an expression of this kind wherein R dash is equal to constant into N0 into delta. Now, if you write the expression R dash in the form of delta by tau, where tau is the time constant, or you can say the lifetime of direct band-to-band recombination, then you'll find that the value of tau is nothing but 1 by alpha n0. So value of tau is equal to 1 by alpha n0, right? So this particular expression you will get once you consider these two equations. All right. So if you consider both of them, you will see that the value of alpha is nothing but, the value of tau is nothing but 1 by alpha n0, right? Now, in this case, your excess carrier recombination rate or excess recombination rate is proportional to the equilibrium concentration N0, right? So let us now see another type of recombination. So the expression for direct band-to-band recombination we already have seen. Now let us see another type of recombination which is known as band-to-band Auger recombination. And in this recombination process, an electron recombines with a hole, and then the excess energy and momentum gets transferred to another electron or hole. So whatever is the excess energy left during the recombination, that gets transferred to another particle. So it's basically a three particle process. So there are three particles, either one electron and hole, and then another electron or hole. So you'll find an electron hole process, or you can see an electron hole process, right? Now, in this case, the recombination rate R can be written as beta p square n plus gamma n square p, where beta and gamma both are constants. And we consider for both hole electron process and electron hole process, the constants are different. So you will get to the expression like this, where R is equal to constant into p square n plus a constant into n square p. Now, if you again replace the values of n is equal to n0 plus delta and p is equal to p0 plus delta, both of them in this equation, you will find an expression similar to this one. So in this case, we are only considering the second term, that is electron hole process, because anyways your holes are minority if you consider an n-type semiconductor. So we are considering an n-type semiconductor. That's why we have reduced the expression of R to a constant into n square p, and then you replace the value of n and p as shown over here, and then you will get an expression for the excess recombination rate. So similar to the previous case, the excess recombination rate is a constant into n square p minus n0 square p0 square, because your R dash is equal to R minus R0. Then you will get an expression of this kind. After replacing the value of n and p, you will get the final value, which is a constant into n0 square into delta. Delta is the excess carrier, right? So in this case, you can see that your excess carrier recombination rate is proportional to n0 square. Previously, it was proportional to n0, right? And in this case, even if you write the expression as R dash is equal to delta by tau, tau is your time constant, then the value of tau in this case will be 1 by gamma into n0 square. as it is shown over here. So this is the expression for band-to-band Auger recombination. So in case of Auger recombination, the excess carrier concentration or excess recombination rate, the excess recombination rate is proportional to N0, proportional to N0 square in case of Auger recombination. In case of direct band-to-band recombination, your excess recombination rate was proportional to N0. Okay, so this is what the expression for Auger recombination. Now we have indirect recombination via deep level that we already have seen for silicon. So in this case, you have EC, then you have EV, and you have an intermediate level EI, right? So the recombination takes place via this intermediate level, and this particular process can be explained by the Schokley-Reed-Hall theory. I am not going in details of that particular theory. Now under under a low injection level, you'll find that the excess recombination rate R dash is equal to theta into Ni into delta, where Ni is nothing but a concentration of deep impurities and theta is a constant. So you can also write this as delta by tau. Tau is the time constant. Then the time constant will be, the expression for the time constant will be 1 by theta n. Now this particular constant depends on the EI value, that is the intermediate level. That particular time constant is now dependent on the intermediate level. Apart from this, we also have a phenomena called surface recombination. If you consider in semiconductor crystal, you will find in the surface the recombination rate is very high because the surface is prone to impurities, and second is a large number of density of states due to the disruption of periodic lattice potential. If you consider the surface of any semiconductor crystal, you will find that the lattice structure, the arrangement will get disrupted near the surface because there is nothing beyond that. So because of that disruption, you will find a large number of density of states between EC and EV. And secondly, the surface is prone to the impurities. So you will get a lot of impurity levels as well. So impurity levels means you will get sites, deep impurity sites for recombination. Now if you see the excess carrier plot with respect to the depth, you will find at surface you have an excess carrier concentration del S, which is comparatively lower than that of the bulk, right? Now the excess carrier recombination rate for surface recombination is proportional to the del S at low injection level. So I am not deriving the entire equation, just take it for granted that Rs dash will be proportional to the excess carrier concentration. So you can write Rs dash is equal to a constant into del S, and if you consider the dimension of R dash and delta S, you will find the dimension for this particular constant is centimeter per second, because for R dash or Rs dash, the dimension is or the unit is per centimeter square second. In case of delta dash, it is per centimeter cube. So for S, the dimension should be centimeter per second, which is a dimension of a velocity, and that particular constant is known as surface recombination velocity. So surface recombination velocity, the value of this particular constant can be varied from 10 to 10 to the power 5 centimeter per second. If the value is low, that means the surface is clean. If the value is high, then the surface is bad. So the constant S in this case, which is surface recombination velocity, will help us to understand the quality of the surface, how the surface is going to be or how the surface behaves. Okay, so this is more or less the entire details related to different recombinations. So we have seen expressions related to different recombination and also have seen the physics associated with. So in the next lecture, we will further discuss the concepts related to semiconductor physics. And now we are slowly going to the device analysis.
So in this lecture, we started with the recombination process and the expressions associated with recombination processes, how we can actually bring in different types of parameters in that expression. We have seen what is Auger recombination and how we can define Auger recombination. We have seen what is indirect recombination and how indirect recombination is different from Auger recombination. And at the same time, we can also see what are surface recombination. So we haven't gone very deep into that surface recombination part, but the concept is very important. At this stage, if you know about these recombination processes, it will help you to understand the physics that is going inside a semiconductor device or in semiconductor device related sensor. So we will conclude this lecture here and we will study more concepts in the coming lecture. So stay tuned.